Bom dia a todos. Good morning, everyone. It's a great pleasure to introduce Professor José María Espinar from the Universidad de Cadiz, Spain. Professor José María Espinar received his PhD in mathematics in 2008 at the Universidad de Granada, and he was a research fellow at the Universidad de Granada, Spain, Paris 7 and Paris Est in France, and also in Stanford University at the USA. In 2011, he obtained a James Simons Chair, founded by the Simons Foundation at IMPA, where he became a permanent professor in March of 2016. In 2017, he obtained the first position at the 2017 National Call Ramon y Cajal in the area of mathematics, joining the Universidad de Cadiz in January 2018. Professor José María Espinar works on geometric analysis, and today he's going to talk about minimal surface from soap films to black holes.
Thank you, Joao. It's a great pleasure to participate in your event. I would like to especially thank to you and to Katie for the invitation. And today my talk is going to be about, as the title says, minimal surface from soap film to black hole. And it's intended for PhD students, so it's not very specific. Also, it's impossible to quote all the people who has been working on this field. So I apologize in advance for those that feel that they are not in the presentation. So do you see my screen, Joao?
Not yet.
So sorry, that this screen that I don't see. I have it here, but I don't know why. No. Sorry for it was all prepared, but I think I made some kind of mistake. It's my first time I do a web seminar, so that's why. So now you see the presentation?
Yes, now is.
Okay, so sorry for the delay. So as I say, it's my fault. So okay, today we are going to talk about this fascinating topic of minimal surface and the interaction between minimal surface and two fields that are soap films and black hole that is in the imaginary of everyone. Okay. So the first thing that we have to know is what these three elements has in common. What they do have in common is this principle of least action that rule nature. So nature is ruled by those actions that economize in the action that they do. So this is a driving principle from the beginning of science. We can quote, for example, some phrase of Leibniz, Euler, more recently a professor at Stanford, Leon Simon, who says that what we often see in nature are those about some configuration that are possible in the field that we are studying, are those that they do have less energy. And what we do understand for energy, it changes, depending on the field that we are talking about. So we are going to focus on minimization problems. Okay, we are going to give some kind of energy. In most of the time in this talk, it's going to be the area. It's going to be considered like an energy, an action. So we are going to try to minimize what are the best shape that minimize this energy. So we can think in nature, a simple example, like for example, the path that ants do when they are looking for food. So at the beginning, probably the path is like crazy, but at some point in time, they will find the shortest path between the 2 points. So what they do is to find the geodesic in mathematical work. Okay, so we are going to focus on geometry and in physics, but in between geometry and physics, we need to use PD. So we are going to focus in geometric analysis. And in the words of Estillao, one of the major exponents on the field, so it's important to relate geometry and PDEs because we need to compute to see how it changed a different shape in Spain. We need to compute the curvature of these objects. So that's why it's so important. Partial differential equation in geometry and geometric analysis, and that's why it's so instrumental in many areas of physics. So okay, so we are going to focus on the first problem. So it's a problem that became interesting by the big names like Euler, Lagrange, or Meusnier in the 18th century, and they study a very natural problem. So giving a curve, so can we find a surface with less area and that boundary? So this is a very natural problem, and this is how the field of minimal surface started. Actually, so we are going to see the relation of this topic, this mathematical problem, with subfields. So this problem was got the attention of Plateau, and so he was a physicist. He studied optics. Actually, he can be considered one of the father of special effect in films. And so he started to study this problem from a physical point of view, and what he did is to giving a curve, say a wire, a closed loop with a wire. He put this wire into water with soap, and he saw the shape that it creates. So, and he hypothesized actually that this shape has the least area, and actually have to be a minimal surface. But we're going to see what is the physical driving principle for this subfield. So subfield, what they do is the following. So suppose you have a wire and you put it in water with soap. So what the soap particle do is the following. They stick to the boundary, and also in the interior, they stick together. So what they do is to minimize the elastic energy, and hence they are going to minimize the area. So in your left, you can see a subfield with that boundary, and in your right, you can see the mathematical solution to this boundary. Actually, they look pretty the same. So okay, so this is the mathematical problem is called the Plateau problem, and it's the following. So given a Jordan curve, we're going to assume that it's smooth and so on. Can one find a surface with that boundary and minimize the area? So this is an important problem. So actually the solution to that problem appeared for the first time, say in 1930, say in the second golden age of minimal surface, I will show later. And the solution was given by Douglas and also by Radon independently, but Douglas got the Field Medal for the solution of this problem, one of the first Field Medals that year. So as we all know, the Field Medal is the highest mathematical recognition that a mathematician can have. So this was an important point in the field of minimal surface, and we know that driven by those experiments of Plateau, that those experiments say that yes, we can have a solution, an experimental solution, but actually mathematically we can also have a solution. So as I say, this is going to be a talk for mostly students. So, but I need to introduce something on Riemannian geometry, some basic stuff on Riemannian geometry in order to understand better the talk. So the first thing that we are going to do, we're going to focus in three manifolds, okay? We're going to remember, so given a three manifold, we're going to endow the three manifold with a metric. There is a way to measure distance, measure vectors. Associated to that metric, we have a connection. There is a way to differentiate vector fields. And associated to the connection, we have a Riemannian tensor, curvature tensor. That is a way to measure curvature. Actually, we see the the expression of the Riemann-Curvature tension that we have there is like to measure the second derivative of vectors in different directions. So if we focus in the example of the Euclidean space with the Euclidean metric, the connection, this nabla here, is nothing but the differentiation, the usual differentiation. And the Riemann-Curvature tension, since we are saying that we are going to differentiate in two different directions, and we know that in the Euclidean space, we can interchange the rule of the different direction when we do the differentiation. So it's going to say that the Riemann-Curvature tensor is 0, but this is no longer true in general manifold, Riemannian manifold. But this is important, is to connect or to bear in mind that the curvature tensor is some kind of measure the acceleration of the vector field of the particle. Okay, so let's go more deeply into the notion of curvature. And the first one is that we all have in our mind the intuition of curvature for a space curve, right? For a curve in the plane, for example. And the way to measure curvature is to differentiate in the normal. Bear in mind that when you are in the plane, for example, the example, and you have a trajectory of a particle, or you are moving with your car, for example, then the velocity is nothing but the first differential of the movement, right, of the trajectory. And the normal is nothing but a rotation of this tangential vector field, of this velocity. And then the variation of the normal is going to be the derivative of the normal that have to do with the second derivative of the trajectory. And that's the way we measure the curvature. Curvature and the second variation and the second derivative of the movement, the trajectory, are going to be related. That's the notion that we experience actually when we are in a car. Or so, for example, when we take a curve that is really steep, so we can feel the force that's driving us away. That's the acceleration that actually translates to a force. So for surfaces, now we need to use this Riemann curvature tensor, right? And the Riemann curvature tensor, what it measures is the deviation of the tangent vector field. So since in a surface we only have one tangent vector field, the curvature is only going to depend on the point and not on the because we only have one tangent vector, one tangent plane at each point. And here we have the three models of surfaces with constant curvature. So we have a hyperboloid with curvature -1, a cylinder with curvature 0, that is the same as a plane, right? We all have we know that if we take a piece of paper, we can curve in a cylinder without deforming the geometry. So we can do it with a piece of paper. So the curvature, the intrinsic curvature, that's important, intrinsic curvature is 0. And the next one, the round sphere. So there's the model for constant curvature equal to 1 or positive. These are the three. And when we move to a three-manifold, now we have more ways to measure curvature. So we have the sectional curvature, that is the one that we have defined for surfaces. That is for a plane, this EI iota means that we are taking a plane into the tiny space of a three-manifold. The tiny space of a three-manifold is a three-dimensional vector space, so we can take three different linearly independent planes. So and each one is going to have a curvature that is going to be measured using the Riemann curvature tensor. Another way to measure curvature is the Ricci curvature. That is a tensor that when we fix one direction, it measures more or less the mean in the other direction. And another important notion of curvature for us is the scalar curvature. It's like the mean of all the sectional curvature in the manifold. So this we are going to, in this talk, we are going to focus mostly in the last one, the scalar curvature. Is probably the most important, and is the one that is going to have more physical interpretation for us. Okay, so now suppose that you have a surface in a three-dimensional manifold. Then a three-dimensional manifold with a metric, is going to induce a metric on this two-dimensional surface. Then we can have this induced metric in the surface will have an intrinsic geometry, as we have seen. There is the Gaussian curvature, and we will have an extrinsic geometry in the same of curve that we have seen before. So, since we are in a two-dimensional surface and we are in a three-dimensional space, we have a normal, and this normal, this variation of the normal, is going to define a self-adjoining operator. So, a self-adjoining operator, more or less, is to say that each point we are going to have a symmetric matrix on the surface. And as we all know from algebra, 101 algebra, a symmetric matrix can be diagonalized. So, and this diagonalization process will give us at each point the principal curvature, this kappa 1, kappa 2. And we all know that a 2 by 2 matrix have two other invariants. One is the determinant, that is called the extrinsic curvature, it's nothing but the product of the principal curvature. And the other one is the mean curvature, that is the sum of the principal curvature over 2. So those are the extrinsic invariant, the extrinsic curvature, because depend on the normal. And the other one, the Gaussian curvature, depend on the metric, on the induced metric. So one important thing is the Gauss equation, how to relate the intrinsic and the intrinsic curvature using the sectional curvature, right? So in the case that we are in a surface in the Euclidean space, the Riemann curvature tensor is 0, and the sectional curvature of this space are all 0. And it say that is actually the real statement of Gauss, because it was studying surfaces in 3, is that the intrinsic curvature, the curvature come from the metric, is equal to the extrinsic curvature, the curvature that comes from the normal. Okay. So let's say we're going to talk about minimal surface. What are minimal surface? So minimal surface are the following. So suppose that you have a piece of surface, okay? And what we want to do is to find the one of minimal area. So when we were in high school and we were studying maximum and minimum, the first thing that we did was to find the critical point. So that's the way we are going to define minimal surface as critical point of the area function. So the way to do that is the way we are going to do that is the following. We are going to take a curve, a surface, in order to see that it's minimal. We're going to do variation, local variation of the surface. So the surface is this red line that is there, this red curve, and the variation are the blue ones, okay? You have a one parameter family of variation. We're going to compute the area of all those variations, and we are going to take the derivative, okay? So this is the next, this thing. So this sigma t are variation of the red line, of the red part. And what we are going to consider is the area of this variation sigma t. And what we are going to say that a surface is minimal if the derivative of this function f is 0 for any variation, okay? So, okay, now we have a functional. We are going so minimal surface are the critical point of this functional. So in particular, if this function is 0 for any variation, we say that the mean curvature is 0 at any point. That's one of the characterization of minimal surface. Okay, that I say minimal, but so far are critical points of the area function. So, for example, an interesting exercise for students is the following: take a graph in R3. Okay, so we know that the area of this graph is given by this integral here, is the square root of 1 plus the square of the gradient, and do variation of that. And if we do variation of that, Lagrange did in 1762, and found that actually, in order that this graph is a minimal surface, we have to verify a second order relativity equation. That is this one. Okay. Well, okay. So far, we have an equation how to find minimal surface. People at the beginning of the around that time we're trying to look for minimal surface. So we are going to see now the first example, how to find minimal surface, okay? So the first one, that actually the only solution that Lagrange could find with this equation was actually the plane, right? The plane is nothing but a linear combination of x and y, and solve this equation, because the second derivative of u are going to be 0. So the plane that actually was found by Euler also in 1744. Around that time, also Euler found the catenoid, right? Also the helicoid. Later, like 100 years later, Scher found another type of minimal surface. So let me explain. So the plane is the trivial one, right? The catenoid is the one that is invariant by rotation. Also, Musnier proved that the plane and the catenoid are the only one invariant by rotation. The helicoid is a surface that is the composition of a rotation and a translation, okay? And the shared surface is the one that in this equation, if we consider separation of variables, so you can find this equation, this shared surface, okay? So, but not many examples were known, actually, from Euler to Scher, not many examples were known. So around this time, the 8040, 8060, more or less, is considered, say, the first golden age of minimal surface, because here, with the work of Weierstrass, Schwarz, Enneper, and so on, so starting to include complex analysis method in the study of minimal surface. So they found what is known now the Enneper-Weierstrass representation, that is that given holomorphic functions that define some certain relationship, they are able to construct minimal surface. And also Svart construct solution to the minimal surface equation using the plateau problem in regular quadrilateral. We're going to see some example next. But it's important. So far, there is another tool here that come into play. That is the holomorphic function and complex and harmonic function in order to represent minimal surface. But so far, it's okay. You can, given a holomorphic function, you can represent a minimal surface, but you don't know how they are. Actually, so we can see here some examples, right? We will say the example is Svart. The Riemann example, that is the one that are foliated by circles and lines on each plane. And the Enneper surface that come from the Weierstrass representation with some specific Weierstrass data. We see the Enneper surface is not embedded. It's immersed, right? It have self-intersection. The other example that we have presented are embedded. So for a long time, actually, people thought that the plate and the catenoid and the helicoid were the only embedded example of finite topology. But we have to wait another century in order to construct embedded example of finite topology. There is a famous Costa example, right? Actually, at the beginning, Costa didn't prove that it's embedded, but it come later with the word of Hoffman and Mix, that it's embedded. Was the next example after the plane, the catenoid, and the helicoid of an embedded, complete, minimal surface in R3 with finite topology. Finite topology means that have finite genus, a finite number of holes, and a finite number of ends. In this case, the Costa surface has genus 1 that we can see there in the middle, and 3 ends. Two ends that looks like catenoid, the top and the bottom, and the middle one that looks like a planar end, like a plane. And later, Costa, Hoffman, and Mink constructed this kind of example with any kind of genus. Okay. So I talked about the first golden age. The second was around the time of Radot, Douglas, Schiffman, where the first one was when Enneper-Weierstrass introduced complex analysis. The second one with the work of Radot and so on that introduced PDE method. And this This one, from the 60s to the 80s, in the Berkeley School, with Osserman, Hoffman, Mix, Rosenberg, Carmo, here, here in Spain, also with Antonio Ros, Lopez, pushing the theory of minimal surface with using all these tools that come from the first and the second golden age, and also improving new tools like stability and so on that we will see next. Around this period, the field of minimal surface experienced a great development. So I'm going to talk about classification of minimal surface, and I'm going to focus on one specific part. It's impossible, as I said at the beginning, to about all the field of minimal surface. So I'm going to focus on one part. So I apologize for those that are not quote in this in all this talk again. But for example, we can say that one of the major classification results recently is the loss and conjecture by Brendan, right? Classifying minimal tori in the three sphere, for example. There are many others. And I'm going to focus on those that have to do with finite total curvature, finite index, stability, and all this stuff. Because, as I said at the beginning, minimal surface are minimum of some kind of functional. So far, I have defined it as a critical point. But now, let me tell you that actually they are local minima. And we're going to talk about stable surface, right? So as we all know, when we have a function in R, we find critical points as zeros of the first derivative. And in order to find the minimums, we do the second derivative. And we look for those points that are critical points so that the second derivative is bigger than 0. So we are going to do the same with those, with the functional defined before, this area functional for this completely supported variation. And we are going to define a stable minimal surface are those that are critical points for the area, that is that the first derivative is 0, and the second derivative satisfies this condition, is bigger than 0. So this condition we can translate in an analytical condition. Schoen and Yao did it, and it tells us that actually the second fundamental form, that is this term here, a square, the Ricci curvature satisfies this integral condition for any function of compact support on the surface. Okay, so it's important to classify this example because when we take limits on minimal surface and so on, more often what we are going to appear is a stable minimal surface. So if we control stable minimal surface, we control the limits of blow-ups minimal surface. So it's important. It's the solution with more structure, say the stable one. It's the one, as Leon Simon said, and the quote that I put at the beginning, is the one that is going to appear in nature, the stable one. So stability, we can rewrite stability in this way. I have to write this second derivative. We can write in this kind of integral, this f times this Schrödinger type operator, L of f. There is the Laplacian plus some kind of potential, right? Actually, this operator, this Jacobi operator or linearized operator of the mean curvature, is called in that way because if we do the first derivative of the variation of the mean curvature of the surface, actually what happens is that the first variation of the mean curvature is equal to this linearized operator. So that's an important geometrical tool. So, but let me, this interesting remark here that, okay, we have this operator that come from this, well known in quantum mechanics as a Schrödinger operator, right? They are important because this, when Schrödinger studied this quantum mechanics, he used the wave equation, how a particle is in the space, and this Schrödinger operator that were the elliptic part is like when a particle doesn't depend on time. So when it doesn't depend on time, the Schrödinger operator is actually this kind of relativity operator that we are considering. So this linked a little bit the theory of quantum mechanics and this stable minimal surface. And actually the physical interpretation was given by Born, and it's like the probability amplitude of this of the particle was the probability to find a particle in the space in some sense. So okay, so the important thing here is that this operator can find a quadratic form, as I say, as a self-adjoining operator in the space, more or less in the space of functions. So as I say at the beginning, the normal define a self-adjoining operator, a time by 2 by 2 matrix, right? Symmetric matrix. So that's a finite dimensional. This one is going to be a quadratic form too, but in an infinite dimensional space. However, using classical theory, we can see that we can do more or less the same that in the case of in the finite dimensional case. So we can diagonalize this index form, and we will have eigenvalues. Okay, that are going to be an infinite number of them, and they are going to grow to plus infinity. So, and we are going to call an operator defined on a surface is going to be stable if the first eigenvalue we order in an increasing order is going to be non-negative. So all the eigenvalues are going to be positive. It's non-negative. Or equivalently, if the index 4 is bigger or than 0 for any function that we plug into this index 4. Okay. What this means? Analytically, as I say, what it means to be operator stable is that all the eigenvalues are bigger or than 0. But geometrically, what it means is that we have a finite dimensional space with so finite index. What it's going to mean is that there is only a finite number of variation that is going to make that the index 4 is negative. Okay. When we translate that into geometry, we say that we only have a finite number of directions where we can deform our surface, and the area is going to decrease. To be stable is that for any direction that we take, the area is going to increase. Okay, that's why it's a local minimum. Okay, so now let's focus on a stable surface. What it means to be stable? Suppose that you have a complete surface in R3 or in any manifold. To be stable means that no matter how big you take your domain, that variation of that domain are going to be stable. Okay. So, and that gives us a lot of structure, I would say. That will imply that you're going to control the topology, the conformal type, the area growth, and so on. So, for example, the first important result in the field is due to Doccarmo and Penn, say that a complete orientable, stable, minimal surface in the Euclidean space have to be the plane. Now, if we move to Riemannian manifold with non-negative scalar curvature, as I say, this is the kind of curvature in the three manifolds that we're going to consider. And we assume that actually we have a compact, stable, minimal surface, we can control the topology and the conformal type. Have to be either a sphere, topological sphere, or a torus, and when it's a torus, have to be flat, intrinsically flat. So that's important because actually that is not longer that say how is the stable minimal surface. It will say in the second theorem by Schrödinger here is that when we have this surface, we are also able to classify the manifold. Not all manifolds are going to support a flat torus with non-negative scalar curvature. Actually, in that case, if the torus is incompressible, so that means that we cannot deform to a point in the manifold. So think if we translate that to curve, if we take a donut, okay, and we take a curve around the donut, So we cannot compress this to a point. For example, in a sphere, and we take any curve, any closed loop in the sphere, we can compress to a point. But in a torus, in a donut, we cannot do that. So it's the same situation for surfaces in three manifolds. So we cannot compress that torus into a point. So in that case, if we cannot compress, what that means is that if we do the formation without breaking it, we can find in that class a surface with least area. So since the surface of least area in that class is going to be a minimal surface, and also it's going to be stable, then we can apply the Schrödinger result. It's going to be a flat torus, and then we can reproduce the process because it's a minimizer. It's even stronger than to be stable. It's a minimizer. So that's the way to prove that. So the existence of minimal surface in a three manifold can actually not only classify the minimal surface, but also classify the three manifold. So in order to study complete surface, showing now with Fisher-Corby, study the same case, but for complete, not compact. And they find more or less the same result. They can control the topology and the conformal type. They were able to show that in a surface that is stable and complete in a manifold with non-negative scalar curvature have to be either conformally equivalent to the plane or to the cylinder. But in the case of the cylinder, despite what happened in the case of the flat torus, they were not able to prove that cylinder have to be flat. Actually, they need one more condition. Is this condition of the integral of the Gaussian curvature have to be finite. And in that case, if they also have that condition, actually, it mimics the case of the flat torus for compact surface. Actually, with the proof that I have to be totally geodesic and the scalar curvature have to vanish along the surface. Actually, this condition was removed recently by Martin Reilly and myself. And now we can mimic the case of the flat torus for complete surface. So, okay, now this is for a stable one. That means that for any bigger domain that we take, it's going to be stable. The first second value is going to be non-negative. But what happened for finite index? Finite index is really interesting in R3 because finite index is equivalent to finite total curvature. Finite total curvature was proved that it's equivalent, more or less, or you can control a lot of the surface because implies that have to be finite topology. Actually, Colin proved that finite topology implies finite total curvature in R3, so it's more or less the same. Actually, we control the conformal type, have to be of the end, have to be punctual end, and we control more. In the case that they are embedded, they have to look like catenoid or plane. Like, if you remember, the case of the Costa surface. So we know that the only one with index 0, Carmo and Penn, is the plane. But for index 1, the only known sample is the catenoid. And for index bigger than 1, we have a gap. And the other one that we know is the Costa-Homma mix that has index 2G plus 3. So in the case of the Costa surface, is genus 1, is index 5. Okay, we have a gap there. So what happened? Do they exist in between? Do we have surfaces in R3 with index 2, 3, or 4? So there was a question around that time, around the 80s. So we have here a plethora of examples of theorems about the classification of finite index. So the first one, Fisher-Corby, Carmo-Penn, Pogolerov also proved that in the orientable case, the only stable one is the plane that we have seen. Actually, Ross proved that result with removing the hypothesis of orientable is true for any stable minimal surface, no matter what, orientable or not. Showing proof that the plane is the only one with finite index and 1m. Lopez and Ross also proved that the catenates at the n-pairs surface are the unique complete orientable index 1 minimal surface. Okay, so the difference here between the catenate at the n-pair and the catenate is embedded and the n-pair is not, right? But are the only one with index 1. So Schoen also proved that the catenate is the only, the unique complete embedded orientable finite index and 2-ended minimal surface. Actually, what he proved is that it's the only one with 2n and finite total curvature, no matter what the genus. But finite total curvature implies finite genus, so it's the same statement. Also, Lopez and Ross proved that the plane and the catenate and the unique complete embedded orientable finite index minimal surface of genus 0. And really recently, Schoen and Maximo proved that this gap that we commented before, actually, we don't have surfaces, complete embedded orientable minimal surface with index 2 or 3. It remained the case of 4. It seemed to be true, but they don't prove it. So it's natural to expect that we have the catenoid, and then we will have the coastal surface. And in between, we have nothing of index 2, 3, or 4 in the better case. So it's a really interesting problem, and this is a really beautiful paper of Schoen and Maximo. So, okay, now existing again, right? I'm going to focus in recent part of existing based on minimax, but I'm not going to talk about, for example, the amazing work of Karen Uhlenbeck. There is minimal spheres that actually she recently won the Abel Prize, or the mixed yaw method in order to find minimizers. So I'm going to talk about yaw conjecture that have been recently proved. And this started with an old problem by Poincaré on geodesic, right? So geodesic is Poincaré make the following question. So given an ovaloid, right, a symmetric ovaloid in R3, if there is always 3 simply closed geodesic, okay? So, and actually he asked, do we have an infinite number of them? So even for a sphere with a, not for the wrong sphere, that we know that any if we cut with a plane passing through the origin, it's going to give an embedded sphere, an embedded geodesic which is a great circle. But for any surface, for any topology, for any geometry that we put in the sphere. So actually, Birkhoff gave the same proof that actually a sphere with a metric has at least one embedded closed geodesic. Okay, he used a minimax method. Then Ballman proved the Poincaré conjecture, and Franz used proof that actually we do have an infinite number of them immersed using dynamical system. It's interesting that these two approaches are two different approaches to the same problem: minimax and dynamical system. So, in analogy with this Poincaré conjecture, we have the yaw conjecture. So, think that minimal surface is the two-dimensional analog of geodesic. So he asked if a 3-manifold contains an infinite number of immersed, not necessarily embedded, minimal surface, right? So this was a long-standing conjecture in the field. Actually, Agnew and Pitts proved that at least you have one in dimension between 3 and 7. Dimension bigger than 7, we have some problem, some issue with the regularity of the surface that we find. So we are going to focus on dimension less than 7. That's perfectly smooth. And following that work, the Marquez and Neves, they implement this minimax method of Agnew and Pitts in order to prove the Wilmot conjecture. But they went further, and actually they were able to settle the yaw conjecture when the Ricci curvature of the manifold is positive using a Frankel type argument and minimax theory, right? But later, with Erie, joining this minimax with dynamical system, the two approaches that we saw before for geodesic, they were able to settle the Yau conjecture for generic metric in dimension less than 7. Again, for dimension bigger than 7, we have some regularity issue. They define the minimal surface, but they cannot be regular. They might not be regular for up to codimension 7. So, but this method led to a student of Fernando, Antoine Song, to settle in his thesis the Yau conjecture in dimension less than 7. So it's a beautiful thesis, and this is the way to do a thesis, right? So it's an impressive masterpiece of mathematical art that Antoine Song did settling this Yau conjecture. He brought together all the tools that the school of Andrea and Fernando developed for all these years in this Minimax, putting all together, also bringing new ideas in the topic in order to settle the Yau conjecture. So, and another classification result is the planar domains, right? There is in R3. There is actually, I would say that we are living the last 2 decades, the last golden age of minimal surface, and it's based in this Minimax school of Fernando, Andrea, and so on, and the word of Colin Mininkosi, how it was used by Mix Rosenberg, Mix Perez-Roth in order to classify the planar domain. The two main ideas that we have in the last 2 decades of minimal surface, I would say, my opinion. So, and this comes from the old theorem of Bernstein that actually the original one is wrong, but Hoff fixed it a few years later, that say that the plane is the only entire minimal graph on R3. So if we take R2 and we consider a minimal graph, entire minimal graph, the only one is going to be plane, okay? And Osserman, in the 80s, conjectured the following thing. It would be really nice to see that the helicoid and the plane are the only embedded, simply connected, complete minimal surface in R3, right? So he described this question as potentially the most beautiful extension and explanation of the Bernstein theorem. So this question was settled actually thanks to the work of Colin and Mininkosi and this amazing one-side curvature estimate that I don't understand, but it's a very difficult theorem in geometric analysis in minimal surface, this one-side curvature estimate. And with this, they were able to prove that actually, if you have a connected, complete embedded minimal surface of finite topology, they have to be proper. So complete and embedded finite topology implies proper. So that's important because Mix and Rosenberg were able to use that this one-side curvature estimate and this statement to prove and settle the Osserman conjecture. Actually, that a complete embedded, simply connected minimal surface in R3 have to be the plane or the helicoid. One of the beautiful theorems in the field. And later, actually, using this one-side curvature estimate and many other techniques, right, a really difficult paper too, by Mix, Perez, and Roth, another amazing paper, that actually they were able to classify all the planar domain. What means a planar domain? So the topology of the surface is a plane removing points, probably an infinite number, okay? But that's the topology of the, and they were able to prove that actually the only embedded sample with this topology, properly embedded, have to be this list of examples that we have seen, the plane, the helicoid, the catenoid, or the Riemann. Actually, they are all foliated by lines or circles. So that's a beautiful classification result of minimal surface. Okay. So we started in subfield, how subfield took us to minimal surface. We have seen some detail on existing classification of minimal surface. And now we come back to black hole, right? So this amazing topic of black hole and how mathematics can help to understand these objects. So it's impossible to talk about the black hole without talking about Einstein, right? So the first thing that Einstein had in mind is that Newton equation describe the events, but don't give you the why. Einstein was really worried about the why how the equation appears. He didn't want to give the equation. He wanted to give a principle from which the equation of the movement of the universe can be derived, right? So that's the motivation, the conviction that he has. So, and the first one appeared with this special relativity in 1905, right? And this is the reflection that he made. So the longer and the more desperate I tried, the more I came to the conviction that the only discovery of a universal formal principle could lead us to ensure results. So that's important. So in this famous paper of 1905, it's not the only one at the time, right? So we know that this is one of the great years in physics by Albert Einstein. So he, in this field of special relativity, he made the following two principles. The principle of relativity is that any two systems moving with constant velocity has the same law of physics. Okay, so this is against the conviction that we have a preference system of reference. So there is no preference system of reference in the universe, and all depends how they move with respect to each other. And the principle of invariant for light speed. So the speed of light is invariant no matter what. So it's always the same. Okay. So far, no experiment. Even some guys claimed, I think a couple of years ago, that they found some neutrinos that traveling faster than the light. So was wrong. So far, no one has disproved this principle. So with these two principles, and based on the mathematical Lorentz, for example, that he used a lot, so he developed the special relativity. But actually, even in the special relativity, tell us that our time change with velocity, that if we move to velocity close to speed of light, our time, how we're spinning our time, is going to be slower than the other one, than people who are not traveling that fast. Or our mass is going to increase. That's why the only particle that can travel to the speed of light is the one that they don't have mass, for example, a photon. But he wasn't convinced. He wasn't happy enough with that theory. Need more, because he wanted to include gravity in this theory. So in 1915, he came with an equivalent principle. That is said, something in his mind would say that the inertia and gravitational mass have to be the same, right? Using the Newton equation and so on. So he came to the conviction that inertia and gravitational mass have to be the same. So that's important, because this equivalent principle say that a gravitational field have to do with the acceleration. Nothing but with it. But we saw that acceleration have to do with curvature of the space. So actually, he linked from one side forever gravity and geometry. So gravity means acceleration means curvature. So he was able to join these two realms forever. Right now, we don't understand special relativity or general relativity without thinking in geometry. But that's okay. So he was able to give the framework, geometry, but the principle. He needs something that explain the equation. And he was able to do this thing using what we have said about nature, the principle of least action. He found an action. Hilbert and Einstein found this action, the Einstein-Hilbert action. And this action, I'm going to not talk very deeply on this, is this function here, this integral. This S here is the, now we have to move to a four-dimensional Lorentzian manifold. In one direction we have time, right? That has to be measured in a special way. And we consider these actions. Then the Einstein field equation are going to be critical point to this, as we did before for minimal surface, for this functional. This L sub m, is the matter field that we have in our universe. Sorry. So the Einstein field equation, we have this 2T. This T is the strength energy tensor, is the distribution of matter and energy in the universe. And the other one is the Hilbert-Einstein tensor. So the solution, the critical point to this energy, to this functional, are the Hilbert-Einstein solution, this matrix that we have here, this G. So in the same sense, is that Einstein, what we found is that it's a principle, it's an action that is going to derive the equation of movement in a space-time. So, okay, so now we have the space-time, we have everything, right? So, but imagine that we do a picture, we freeze time. So what we're going to see is a three-dimensional, okay, three-dimensional manifold inside our form manifold, okay? And this is going to be called an initial data set. Okay, and then the strength energy tensor can be seen only in this slice, in this initial data set, and we will have the local mass and the local momentum. It's nothing but to see this strength energy tensor in this slide. And we're going to assume that we have the dominant energy condition. This is a condition that is physically makes sense, right? It's only saying that the flowing of matter, of energy that we have in our light that doesn't travel faster than light. That so far is the way we experience that. Okay, that's mathematically what it says that this the norm of the local momentum is less or equal than the local mass. Okay, so but it's impossible to talk about general relativity without to talk about black holes, right? So black holes are the singular solution to the Einstein field equation. And actually, Einstein only found the trivial one, the Minkowski space, right? The one that is fine, that is flat, and so on. But shortly after, 1 year after, Schwarzschild found actually a explicit solution to the Einstein field equation with a black hole. Okay, so that's interesting. So actually, there's a lot of work in black hole, actually in singularity, because they are singularity. Actually, there's nothing prevent from the equation, from a mathematical point of view, that this equation you can see or not see the singularity in the sense that they are naked or not. So when they are naked, is that you can see singularity. So far, we haven't experienced naked singularity. Okay, we have seen no naked singularity. No naked means that it's something that prevents us to see the singularity. And what prevents us to see the singularity is a black hole, is the event horizon of a black hole. So for those that like the science fiction and like the films, so that picture, the summation picture, is taken from the Interstellar, and that's the event horizon of a black hole. So, and actually, this is a real photo of a black hole. Actually, we have seen 3 years ago, 4 years ago. Now, this is the first image of a real black hole, and we can see how is the topology. It's more or less like a sphere, and we will see that that's true actually, yeah, mathematically and physically, using this stability assumption. So, okay, so black holes are we know by a black hole is the event horizon of this. The black hole event horizon is the part that the light cannot escape from there. Okay, mathematically we call this marginally outer trapped surface, or MOTS. Okay, so it's the mathematical replacement of black holes. I'm going to go a little faster in this part. Is the how to define the MOTS. And the idea is the following, okay? So a MOT is going to be a surface in our initial data set that is going to be contained in our space-time. So we have two second fundamental forms, the second fundamental of the surface in the three manifold and the three manifold in the four manifold. Now we can define like a mean curvature of this surface is this small h. There is the trace of the sum of the two second fundamental forms. There is the usual mean curvature of the surface plus the trace of the second fundamental form of the initial data set in the four manifold. So we are going to see there is a MOT, it's imaginary outer trapped surface, if this little h is 0. And we are going to define a apparent horizon if actually it's a mod and there is no other mod they're going to contain this mod in some sense. It's like a minimum between all the mods. Okay, so in some sense, an apparent horizon is going to be stable in this sense. Okay, but look, one detail. When the trace of the, for example, imagine that the initial data set is totally geodesic in our four manifold, then the second fundamental four is 0, this B is 0, and in particular, this trace is 0. But when that happens, actually, the condition to be imaginary of the trapper means that the surface is a minimal surface. That's why these two black hole and minimal surface are so related. So, for example, Hawking proved that the cross section actually, when we take a picture and we see a black hole, the topology have to be to a sphere. Makes sense with make an analogy with the result that we have seen previously of Schoen and Simon about the topology of a stable, compact, minimal surface in manifold with non-negative scalar curvature, right? And actually, this theorem in Hawking, you can see the picture in your right. It's true, right? So far, it's true. So, okay, another important issue in general relativity is the positive mass theorem, right? So the positive mass theorem say that under natural physical conditions, say the dominant energy condition, the total mass of our universe is bigger or equal than 0, right? So that's something that have to be true because we experience our universe in that way. So there are other energy conditions like the strong energy condition, but that we experience on sand, but have contradiction, for example, with things like dark matter and so on. So mathematically and physically, there are many different energy conditions, but this is probably the most interesting for us, the dominant energy condition, because in the case, for example, of your integral data set is totally geodesic, actually it's going to translate to the scalar curvature bigger or equal than 0 and minimal surface when we are talking about black hole. So the positive mass theorem was a conjecture by Hawking and actually was proved first by Sean Yao using minimal surface up to dimension 7, again, because of a problem of regularity. Witten, 2 years later, do a different method for any dimension, but assuming that the manifold is a spin. And recently, 2017, Chen and Yao claimed that proved the general positive mass theorem using minimal surface with no restriction on the dimension. Okay, I say claim because so far I don't know if the paper is published. I say it's in archive, but I don't know if it's published. Or another interesting thing about talking about the mass is the Penrose inequality. That Penrose say, okay, so you have a manifold, a space-time have to be your mass, but imagine that you have a black hole. Then the mass have to be bigger than some quantity that depends on the black hole. And that quantity is the area, is this quantity here, the square root of the area over 16 pi. So the Penrose inequality say that if you have a black hole with some area, actually the mass, the ADM mass, the total mass of the universe, is going to be bigger or equal than that quantity. So actually it was proven by Huisken and Manek using inverse mean curvature flow, and Bray using a conformal flow metric. Okay, so this is part, this is not all, this is a field that is very appealing in any direction that you take. There are many other directions that I didn't have time to comment. For sure, this is a history that is not going to be over, and it will continue. This is all.
Okay, Professor José Espinar, thank you very much for this very, very nice talk. And I would like to ask the audience if there are any questions or comments. And I can see a lot of comments there. So let's see if I have a question here. I have not a question, but Can you say a few words about your current work on minimal surface? I've seen that you are working on Lawson conjecture and also Schiffer conjecture and the relation between both. Maybe just a few words.
Only a few. Yeah, right now I would like to. There is I've told about the Lawson conjecture by Brendel, right? There is another one. There is the critical catenate conjecture. There is say that the only free boundary minimal annuli embedded in the ball have to be the catenate, right? Have to be the critical catenate. You can see that, or you can translate that problem into overdeterminate problem into the sphere, as the Schiffer conjecture for annular domain. So I have been working a lot, but without any success so far on this project. Right now, it's true that I'm working in this say Schwarzschild. I'm working on free boundary minimal surface and the Schwarzschild space-time of any dimension with Professor Ezequiel Barbosa. We are soon we will post, I hope, some result in archive. But is that there are many directions here. There are many open problems, but this one about the critical catenate, I think for me is really interesting. It's one of the. This is another one related to the index 4, also because I've been talking about index. This gap of the paper of not gap, this showed us some maximum Otis and David that they didn't prove that there are not minimal surface index 4 in R3. I think that's a beautiful paper, and it's a case that is worth it to study. Or the index 4 conjecture for the catenate, right? So the only free boundary minimal surface in the ball with index 4 have to be the critical catenate. I do have more problems in that solution. So,
what's your feeling about the index 4?
The index 4 minimal surface in R3 or free boundary in the ball?
The both, maybe both.
I think that for the critical catenate have to be the critical catenate, right? Index 4 implies critical catenate. There are no index 4 in R3 embedded. Complete embedded index 4, there is no. That's my feeling.
Okay. So let's see. I have a question by Yuri Dumares Sobral. Do you know whether the tears of wine formed on a glass of wine are minimal surface?
Excuse me, can you repeat?
Do you know whether the tears of wine formed on a glass of wine are minimal surface? And there's also a comment. They are formed by gradients of surface tension due to evaporation of the alcohol of the wine.
Wait, can you read because I didn't understand. Can you read the?
I will read it again. Do you know whether the tears of wine formed on a glass of wine are minimal surface? There is a sequence of the question. They are formed by gradients of surface tension due to evaporation of
you mean the Lawson surfaces in the sphere?
No. Just the tears of wine formed on a glass of wine are minimal surface.
No, I don't think they are. They should be a surface whose mean curvature. Actually, the mean curvature depends on the height function. These are a tear, like a drop, are surfaces whose mean curvature depend on the height function, on the angle function, are not minimal. They're studied. So drops. So these kind of drops are you can actually. Professor José Antonio Galve and Pablo Mira have some papers on this thing, but no, they are not minimal.
Okay, I have another question here. Alan Koch-Alenka. What's the formal definition, the mathematical definition, I believe, of black holes?
Well, the formal definition is that everyone has a formal definition. That it's not It's not an easy. Actually, this apparent horizon that I defined is, say, the most used right now as a mathematical tool in order to study the horizon of a black hole. So this is the one that I gave. It's the most used. Is that here? If you are interested, the work of Schoen with Espinar, who was a student of his, who was at Stanford. He studied a lot this field, this specific field, the modes and apparent horizon and so on. Actually, there is some new Espinar and some other collaborators, many other collaborators have been working on this very recently.
Okay. So, is there any more questions or comments? Okay, if not, I would like to thank again Professor José Espinar for the nice talk and to accept our invitation. And now
Thank
we're
you,
going, if you want to say a few words to finish, we are going to have a break now, and then we will resume with the workshop.
Thank you again. It's for me a pleasure always to participate in an event. That the only thing that the next one is going to be there, right? I will be there. I hope so.
Yeah, we're going to. Sure. So, thank you very much. Thank you all for attending the plenary talk, and see you soon. Bye-bye.